For example 2, when it says which point is a solution to this system, well, the first thing I'm going to do is I'm going to isolate these. I'm going to say, well, this can be my equation 1, this can be my equation 2. So for the first one, I'm going to have to divide everything by 2 and say that y is going to equal 1 over 2 x squared plus 2x minus 3. And my second equation, y2, is going to equal x plus 1. When I graph it out and look for the points of intersection, I can see 2 of them. The one on the left, I get -4 and negative 3. And the one on the right, I get 2 and 3. D is the only one that matches. For example 3, I'm going to isolate in the first equation, so I'm going to first move that 10 over and say that this is going to now become plus 14. And then I'm going to divide everything by 2, which means that y1 would equal 2x squared minus 4x plus 7. When I graph both these into my calculator, because the second one is already isolated, I can only see one line. So it looks like there's infinitely many. Well, how can I confirm that? Well, this is already in general form, so I just got to turn the second one into general form. I'm going to say that y is equal to 2 times, when I square this, x squared minus 2x plus 1 plus 5. Y is equal to 2x squared minus 4x plus 2 plus 5. Y is equal to 2x squared minus 4x plus 7. And I can see that they're equivalent equations, just in 2 different forms. There is, in fact, infinitely many solutions. For example 4, we have to write a system of equations that is indicated by the graphs and then solve the system to the nearest tenth. Well, first, if I have any linear function, I need to remember from grade 10 that that would be in the form of y is equal to mx plus b. M is the slope, and b is the y-intercept. So when I take a look at this, I have a y-intercept, or b value, of 2. When I go to the next point, I had to go down by 3 and right by 1 to get there, which means that my slope would equal -3 over 1, or just -3. So I can say that my first equation, y1, is equal to -3x plus 2. For the second equation, I have a vertex of this quadratic at the point of 2 and 1. There's my p and q values. I have another point that it goes through. In this case, it's the y-intercept at 0 and -1. There's a possible x and y, which means that if y2 is equal to a bracket x minus p, which we've discovered in this case is 2 squared plus 1, I can sub in for y the -1 is equal to a bracket 0 for x minus 2 squared plus 1. I'm going to subtract 1 from both sides and get -2 is equal to, well, 0 minus 2 squared is going to be 4a's, which means that a is going to equal -2 over 4 or -1 over 2. And my second equation, y2, is going to equal -1 over 2 bracket x minus 2 squared plus 1. when I graph this out on my graphing calculator, I can see that there's actually another point that would stretch down here where they're going to cross. So there's actually two solutions in this case. They cross at the points of 0.6 and 0.1, which we can see right here, and then they cross again at the points of 9.4 and negative 26.1. For example 5, when we graph these out on our calculator, we can make a rough sketch of what these look like. So I have my first equation is going to look something like this. And my second equation is going to look something like this. When I solve for the points where they intersect at negative 2 and 2 and positive 2 and 2. How could I transform one of the graphs so that the graphs do not intersect with each other? Well, if I'm transforming the first graph here, then I could just move it so that the vertex is below the other vertex because the other one's opening up and this one's opening down. I could say that as long as I picked a q value other than or below negative 6, like y is equal to negative 0.5 x squared minus 7, they're never going to cross. In the second case, because it is narrower than the other one, I don't even need to move it up or down. I could just say that if this one was opening downwards instead of upwards, they would never cross. So I could say that if I change the second one to y is equal to negative 2 x squared minus 6, once again, they will never cross. How could I transform one of the graphs so that they intersect at exactly one point? Well, the one point they would intersect would be at the vertex. They already have the same p-value, it's a p-value of 0, which means as long as they have the same q value, this is going to work. So I could take the first equation, and then I could say that if it was y is equal to negative 0.5 x squared minus 6, then it's going to match the second one and it'll touch once. Or, for the second one, I could say that's going to be y is equal to 2x squared plus 4, and the same thing would happen. If I'm putting a system of equations into context, two divers start their dives at the same time. One diver jumps from a 1 meter springboard, the other one from a 3 meter springboard. Their heights above water are plotted over time. Which system could model a scenario and why? Well, I'm going to start by saying which ones couldn't. In this case, system B can't. I know that because it has one of them starting at a height of 0, but it says that the heights are 1 and 3. Well, system C also can't because they're both starting at 0. And system D can't because they're starting somehow underneath the water. So system A is the only one that actually makes sense. Now, why is it that there is no intersecting point on this? Well, realistically, the reason is gravity. Based on the way that gravity works on matter in, a theoretically frictionless environment, if I have two people jump off at the exact same time, but they jump at different heights, they're both going to come up and both go down at pretty much the same rate, so they should keep approximately a similar distance between them at the same point in time all the way through their fall. The last part, if I'm applying the systems, in this case, suppose that for one stunt, two circus performers are launched towards each other from two slightly offset seesaws. The first performer is launched, and 1 second later, the second performer is launched in the opposite direction. They both perform a flip and give each other a high five in the air. Each performer is in the air for 1.5 seconds. The height above the seesaw versus time for each performer during the stunt is approximated by this parabola here, and their paths are shown on the coordinate grid. Well, if they both reach the same height and they're both in the air for 4.5 seconds, that means that the A value has to be the same in both cases, because it's going to create the same parabola. They're just going to be offset. So then I can pull from the information that I have. Well, I know that the first one has a point of 0, 0. It starts at 0 seconds at a height of 0 meters above. From the parabola information, I can confirm that I hit a maximum point of 4.5. And my p-value should be halfway between my two x-intercepts. That's going to be at 0.75. So now I have an x, y, a p, and a q. I can solve for this one. I can say that for y1, it's equal to a bracket x minus 0.75 squared plus 4.5. Or that 0 is equal to a bracket 0 minus 0.75 squared plus 4.5. Negative 4.5 is going to equal negative 0.75 squared, gives me 0.5625 A's. And when I divide both sides by 0.5625, I get negative 8 is equal to A. Which means that my first equation, y1, is going to be negative 8 bracket x minus 0.75 squared plus 4.5. My second equation, it actually tells me right in the word problem. This guy is launched 1 second later and it keeps the same shape, which means that everything here is just 1 unit to the right of where it finished. 1.5 becomes 2.5. This guy started at 0, this guy started at 1, which means all I'm doing is I'm adding 1 to my p-value. Negative 8 bracket x minus 1.75 squared plus 4.5. I can solve this using technology. I'm going to put in both my equations. I'm going to use that grid that I have up at the top here for reference for reasonable window settings. So I'm going to say that my window settings are going to be -1, 3, and 0.25, and -1, 8, and 1. And when I graph it out, I get something that looks similar to what I have up on the grid. And I get them crossing at 1.25 and 2.5. If I'm putting the solution into context, then I'm just going to write a sentence. The performers high-fived at a height of 2.5 meters, 1.25 seconds after the start of the stunt.